Hello students, we have already learned about the electrochemical cells, different types of electrochemical cells, electrode potential and various formulas like Gibbs energy formula and Nernst equations which are used in electrochemical calculations. So now today we will again take a recap of some key equations and electrochemical conventions, and then we will take some numericals and then we will solve those numerical problems. Electrochemical conventions and notations. So in general, all the electrochemical cells are having two electrodes. One is known as anode, another one is known as cathode. These electrodes are dipped in some electrolyte solutions, and the electrode with the electrolyte solution is known as a half cell. When we combine two half cells, this will give a complete electrochemical cell. Then in second, if reduction occurs at an electrode, it is called reduction electrode or positive electrode, or it is also known as cathode. If oxidation occurs at an electrode, it is called oxidation electrode or negative electrode or anode. Oxidation and reduction potential values of an electrode are numerically the same with opposite sign. As in electrochemical series, all the values are given in terms of reduction potential only. If electrode is having ability for the oxidation, the reduction potential value is become negative, and if it is having ability for the reduction, the reduction potential value will be in positive. Like if a value of copper is 0.34 as it is given in the electrochemical series in positive, so it is having tendency for the reduction. But if we want to take the oxidation potential value for the copper, then it will become minus 0.34. So all the values according to IUPAC which are given in the electrochemical series are in terms of reduction potential only. If we want to know the oxidation potential of those electrodes, then all the values are the same, only the signs will be changed. Like the values which are in positive will be changed into negative, and the values which are in negative will be changed into the positive. The interface across which a potential developed is denoted either a single vertical line or a semicolon. Interface across which potential developed, that means electrode and solution, because the electrical double layer is formed between the electrolyte solution and the electrode. So like if a copper electrode is dipped into the copper sulfate solution, then we will show the half cell by writing Cu, a line or a semicolon, and copper sulfate next to it. In bracket the concentration is given. So this is a half cell. Then representation of a cell will have the oxidation electrode anode on the left hand side and reduction electrode on the right hand side. That means if we are talking about the Daniell cell in which the zinc is anode and copper is cathode, in that case the zinc will be placed on left side and copper will be placed on the right side. And how we will write the complete cell representation? Zinc line, zinc sulfate, then concentration of zinc sulfate, then two lines shows the presence of a salt bridge. This is interface between the zinc sulfate and copper sulfate solution. If a semi-permeable membrane is used to separate these two, then it is also shown by two line, or if a salt bridge is there, it is shown by a two line. So it is the junction between the two half cells. Then electrolyte solution of copper sulfate, concentration of copper sulfate, then a single line and copper electrode. So by this way electrochemical cell can be represented and with the representation it is clear that the metal which is having left side will act as anode and the metal which is having on right side will act as cathode. Oxidation on left side and reduction on right side. The EMF of cell is represented by E cell is equals to ER minus EL, where R represents the right and L represents the left side, means cathode minus anode. Now by taking an example, the previous slide should be clear, like design electrochemical cell in which each of following reaction occurs. Ce4 plus aqueous, that means aqueous solution of a cerium salt, plus Fe2 plus aqueous gives Ce3 plus aqueous plus Fe3 plus aqueous. So how we will write the electrochemical convention for this cell? During the representation, first we have to check that which is going to oxidize and which will going to reduce. Like here, the Ce4 plus is converted to Ce3 plus. That means Ce4 plus is getting reduced to Ce3 plus. Reduction takes place at Ce. Whereas Fe2 plus is converted to Fe3 plus. That means oxidation takes place at Fe2 plus. So, according to the rule, the Fe will act as anode and Ce will act as cathode. So, we will place the Ce on right side and Fe on left side. So, first Fe2 plus a line, then Fe3 plus dotted two lines or two lines shows salt bridge, then Ce4 plus a line and Ce3 plus. By this way we will show the cell. And of course, as we know that Fe undergoes oxidation and Ce undergoes reduction, so we can also give the equations for these two half cells. So by this way we can easily write a convention for the electrochemical cell which is given in the question by the reaction. Similarly, E naught of the cell can be calculated by putting the values of anode and cathode, and then after the calculation we will get the value. The second example, for the concentration cell below, determine the flow of electron. Here the concentration cell is given. In this case, Fe is on left side and another Fe is on right side, but the first side is having 0.01 molar concentration and the right side is having 0.1 molar concentration. So only the difference between the concentration. If we are not going to check the concentration, then only from the convention of the representation of the electrochemical cell, it is clear that the concentration where the concentration is 0.01 is on left side, so this will act as anode, and where the concentration is 0.1 will act as cathode. So in this cell reaction, electrons are transformed from left side to right side, because during the oxidation the electrons are removed and during the reduction the electrons are consumed. So here it is clear that the electrons are moved from the left to right, and in always if electrochemical cell representation is given, it is always happen that electrons are moved from the left side to right side, because left side is having anodic chamber and right side is having cathodic chamber, and always electrons are moved from anode to cathode. Some key equations like Nernst equation of an electrode, we already derived this equation. If we want to derive the Nernst equation for a galvanic cell, then as we know a simple formula, that is E naught of cell is equals to E naught cathode minus E naught anode. So here we will put the values of two different half cells in that formula, and after rearranging the formula we will get the final formula for a galvanic cell, which is E cell is equals to E naught cell minus 0.0591 upon n log m1 n plus upon m2 n plus. These two are electrolytic concentrations. M1, here M1 is anodic side and M2 is on cathodic side. So you can also write the concentration of the electrolyte on anodic side divided by the electrolyte on cathodic side. So by this way we can calculate the problems related to the galvanic cell. Then Nernst equation for equilibrium constant. At equilibrium E cell will become 0 because the forward reaction will be equals to reverse reaction. So E cell will become 0, and then 0 is equals to E naught cell minus RT upon NF log Kc. The Q, which was earlier used in a Nernst equation, which is reaction quotient, will be converted into the equilibrium constant because we are deriving the equation for the equilibrium constant. Then on rearranging and putting values of F, T and R, the final equation will become log Kc is equals to N E naught cell divided by 0.0592 volt. So by using this equation we can calculate all the problems related to the equilibrium constant. These are other equations which are useful, and we have already derived all these equations. Let's start the numerical problems. The first numerical is related to the calculation of cell potential. That means if the values are given and in question it is asking to calculate the cell potential. In that case we will use the formula for galvanic cell, Nernst equation for galvanic cell. So here the question is given, represent the cell in which the following reaction takes place. Mg plus 2Ag, the concentration of silver is given 0.0001 molar. This gives Mg2 plus, which is having a concentration 0.130 molar plus 2Ag solid. That means the cell is having Mg and Ag as electrodes and silver salt as electrolyte and Mg salt as electrolyte. So first we will write the cell. So cell can be written as Mg, Mg2 plus. This shows that Mg is on left side, so it is acting as anode. From the formula, from the reaction, it is clear that Mg is converted into the Mg2 plus. That means here the oxidation occurs. And on the silver side, the reduction occurs because silver is getting reduced from Ag plus to Ag. So this is the cell. After writing the cell, it is clear that Mg and Ag, where we will put the values of the concentration. So by putting the values into the Nernst equation for galvanic cell, E cell is equals to E naught cell minus RT upon 2F log Mg2 plus upon Ag2 plus whole square. Because here the value given is 2. 2 moles. So we will put a square sign here. Then after putting the values and calculation, we will get the value 2.96 volt. This is the answer. So if in a question, if we have to calculate the cell potential, first we will write the cell by the convention method, and then we will find that where the oxidation occurs and where the reduction occurs, and then accordingly we will put the values of concentration and E naught values. E naught values may be given in the question, or maybe you can take these values from the electrochemical series. In second type of example, it is the example of calculation of equilibrium constant. It is related to the equilibrium constant where the E naught value, where the E cell value will become 0, because at equilibrium the forward and reverse reaction will be equal, and in place of Q we will put the Kc. So this is example which is given here. Cu and Ag is having act as electrode. Then E naught cell we can calculate from taking the values of copper and silver, and then E naught by putting the values into the formula. So by this way we can calculate the Kc will become 3.92 into 10 to the power 15. In third example, calculation of standard Gibbs free energy change. This is example of calculation where the Gibbs energy change is asked. The standard electrode potential for Daniell cell is 1.1. Here the standard electrode potential is given. We have to calculate the standard Gibbs energy. For the standard Gibbs energy formula, delta G naught is equal to minus NFE naught. So here the E naught is given and we have to calculate the delta G. N and F. N is number of electron transferred, and F is the Faraday constant. So here 2 electrons Zn will be converted into Zn2 plus and copper 2 plus is converted into the Cu. So 2 number of electrons are transferred during the process, and by putting these values we can calculate the delta G naught for the reaction. So these are the 3 examples. The first one is calculation of cell potential, second calculation of equilibrium constant, and third calculation of standard Gibbs free energy. Next example is calculation of electrode potential at different concentration. Electrode potential, that is the value of a single electrode. That means it is the calculation for a half cell only. The key equations, the first equation which was given in the section of key equations. So as you know that in electrochemical series only the standard electrode potential is given. Standard electrode potential, that means at a fixed concentration, at the unit concentration. So here if the concentration is changed, then what would be the electrode potential? How we will calculate it? Here example is given for the zinc, and the standard electrode potential, as we know, for the zinc is minus 0.76 volt. Here in the question it is given that what will be the potential at 2 molar concentration at 300 Kelvin. Means if we are going to change the standard conditions, the concentration, the temperature, then what happens? So by using the Nernst equation for half cell we can calculate the value. So here the solution is given. This formula will be used, and then by putting all the values we can calculate the value of electrode potential at different concentration and at different temperature. So with the help of this formula we can calculate the electrode potential at any concentration and at any temperature. Next example is calculation of ionic concentration. That means if the ionic concentration of one electrolyte is given, then how we will calculate the concentration of the other electrolyte. The example is copper ion concentration in a copper silver electrochemical cell is 0.1 molar. If E naught is equals to 0.8 volt for silver and E naught for copper is 0.34 volt, the cell potential at 25 degree centigrade is 0.422 volt. Find the silver ion concentration. Here the electrodes are given, standard electrode potential of both electrodes are given. Also the copper electrolyte concentration is given. Then how the silver electrolyte concentration can be calculated. Here we are having two tasks. First, to decide that which one will act as cathode and which one will act as anode. After that, we will calculate E naught of the cell. We will write equations for the cell, both half cells, and then we will put the values, because knowing the anode and cathode is very important. Once we know which one will act as anode and which one will act as cathode, only then we can put the values accordingly in the Nernst equation. So here the silver is having value 0.8 and copper is having value 0.34. More positive value will act as cathode, more negative value or less positive value will act as anode. So always the metal which is having more electrode potential value will act as cathode, and the metal which is having less value will act as anode. So here silver will act as cathode and copper will act as anode. So now we know that which one will act as anode, which one will act as cathode, so we can calculate the E naught of the cell by putting the values in this formula. So this will become 0.46 volt. Always for a cell, this value should be positive if it is a galvanic cell. So here the positive value. If in your calculation the value becomes negative, then it is clear that you are doing some mistake and you are having confusion in taking anode and cathode. So you can clear your problem. Then after calculating the E naught value, the second task is to write the balanced chemical equations. Here this one is the overall reaction, where as we know that where oxidation occurs and where reduction occurs. The oxidation occurs at copper and reduction occurs at silver. So obviously Ag plus will be converted into Ag and copper will convert it into the Cu2 plus. Here in case of copper the oxidation occurs and in case of silver the reduction occurs. After that we will balance the equation. So for balancing the equation, as silver is having one positive charge and copper is having two positive charge, so we will put the value 2 in front of the silver. This is the complete equation. After that we will simply put the values into the Nernst equation. In Nernst equation, except the concentration of Ag plus, we will know all the values. After that, on calculation, the answer will become 0.0722 molar concentration. So this one is the concentration of the silver electrolyte in the cell. So by this way we can calculate the ionic concentration of any one electrolyte if concentration of other electrolyte and other values are given. Next is some numerical based on the concentration cells. As the concentration cells are having slight changes from the normal Daniell cell or normal galvanic cell, that normal galvanic cell is having different electrodes, but here the electrodes and electrolytes are same, only the concentration of the electrolytes are different. So by taking some examples of concentration cell, the calculation related to concentration cell will be more clear for you all. So calculate the cell potential for a concentration cell with 2 silver electrode with concentrations having 0.2 molar and 3.0 molar. For this, first we will write the reaction and then we will write the cell diagram. So here the reaction is Ag2 plus 2 electron gives Ag. This is a simple reaction. It is always for all type of the same for all type of the concentration cells. Then cell diagram. What happened in case of cell diagram? As we know that on left side the low concentration and on right side we will always write the high concentration, because low concentration will act as anode and high concentration will act as cathode. So here this one is the concentration cell diagram. After that we will put the value into the Nernst equation, where E is equals to E naught minus 0.05922 log 0.02 divided by 3.0. So this is the concentration 0.02 and 3.0. These two are concentration of anodic and cathodic side. After that, E naught is 0 for the concentration cell, as both anode and cathode are same and both are having same electrode potential. So after subtracting we will get a value 0. So E naught will be 0, and then we can calculate the value, which will become E is equals to 0.0644 volt for this equation. Next is calculate the concentration of unknown given the equation below and a cell potential of 0.026 volt. So what is unknown given here? The concentration of Ag plus. Here it is again a concentration cell. On right side it is having a concentration 1, on left side it is having a concentration of unknown, and we have to calculate the unknown concentration. Again we will put the value into the Nernst equation for a galvanic cell. E naught will be 0, and after putting the values we will get the concentration of Ag plus on left side. Always this value will be lower on right side value. You can check your answer also, because it is always fixed that on left side the concentration will be lower and on right side the concentration will be higher. So in case of concentration cell, all the calculations are as similar as the case of galvanic cell. Only the difference here is E naught will be equals to 0, because both the electrodes and electrolyte system are same. So the electrode potential will be same, and on subtracting the value we will get 0. So by putting the E naught value 0, we can calculate all different type of numericals for concentration cell, same as in case of galvanic cells. So this is all for today. Today we discussed about the electrochemical conventions and how to write the electrochemical cell, how to write the equations, how to determine that which side will act as anode and which side act as cathode, what are half cells, how these half cells are joined together to form a cell, and how we will put the different values in different equations. We also discussed different key equations which are useful to solve the numericals based on electrochemistry, and now I hope that you all know all the formulas and convention and all the rules to solve the numerical problem based on electrochemistry. So this is all for today, and thank you all for listening carefully. So from next class we will start the corrosion part. Thank you all.